So here's a problem from the 2010 AP Calc BC exam. This was a calculator question back in 2010. There were 3 of them back then. And it's a parametrically based problem. And if you read the setup for it, it tells us that we've got a particle moving along a curve. Its position at time t is given by x of t for the x component, y of t for the y component. They do provide us with x of t, right, this little polynomial right here, but then they don't give us y of t. They go on to say that x and y are going to be measured in meters, time is measured in seconds, but then they do provide us with the y component of velocity. So they give us the rate of change of the y component of position, but not the y component of position itself. So we'll just have to kind of make sure we recognize as we progress through this problem, we have access to the x component of position, but we only have access to the y component of velocity. And if we check out what we're asked to do in part A here, we're asked to find the speed of the particle at time t is equal to 3 seconds. So speed is going to be the magnitude of the velocity vector. And so what I did to begin with here is I found my velocity vector at time 3. And the x component of velocity is just going to be dx dt, the rate of change of the x component of position evaluated at 3. Well, the derivative of this is 2t minus 4, right? A couple of power rule applications there. And you get 2t minus 4 for the x component of velocity in general. Well, when you evaluate that at 3, 2 times 3 minus 4 is going to end up giving you 2. Then for the y component of velocity, we already have access to that. There's no need to take a derivative here or anything. We just have to evaluate this derivative at 3. And so 3e to the 3 minus 3 and then minus 1 is actually going to simplify down to 2. So you've got an x component of velocity being positive 2, a y component of velocity being positive 2. I'm going to try to draw the velocity vectors. That's supposed to be my x component of velocity and my y component of velocity. Both of these have a magnitude of 2, right? So 2 units here, 2 units here. The speed of the object at this time is going to be whatever the magnitude of this resultant vector is. And so this resultant vector, we're going to find its magnitude, the hypotenuse of this little triangle I just drew essentially, by using the Pythagorean theorem. And so if you use the Pythagorean theorem with these as the lengths of the legs of your triangle, you end up with a speed of 8. And I guess I could have put some units here. They did provide us with that. Wouldn't have really cost me within this problem, but it's meters for time, meters for distance, and then time is measured in seconds, so meters per second I can tack on there if I would like. If we go ahead and move to part B, part B wants us to find the total distance traveled by this particle on the interval from 0 to 4. Well, with the one-dimensional motion problems, which you have probably done before, you integrate speed, you integrate the absolute value of velocity to determine total distance, and you do that across the appropriate interval of t. And if we apply that same idea here, we just found speed on the previous screen, and the way that we found speed was by finding the magnitude of the velocity vector. Well, if I keep that general without putting specific numbers in place of dx dt or dy dt, like in the case of part A, we had evaluated this and this both at 3. But if I keep it general, dx dt squared and dy dt squared in this spot, I can substitute in what we had for dx dt from the previous screen, right? The derivative of this is going to go in place of dx dt. This is already dy dt. If I evaluate this on the calculator, and this is tricky to input to the calculator, there are a lot of grouping symbols that you have to watch out for here, but if you input this to the calculator and use the calculator's capability of numerically estimating an integral for you, you end up with 11.588 meters that the object traveled over the course of the first 4 seconds that it was moving. In part C, it went and asked us to determine when the line tangent to the path of the particle is horizontal. So when you're determining tangent slopes to plane curves, parametrically defined curves, you have to find your rate of change of y with respect to x. We're still finding slope the same way. These things are still graphed in the xy plane, so we still need a rise and a run, a rate of change of y divided by a rate of change of x. The way that we find that with parametrically defined curves is we take dy dt and we divide by dx dt. And so if we build that expression for this specific plane curve, we end up with dy dt being in the numerator here, dx dt being in the denominator. Well, we want to know when the slope of the tangent line is going to be 0. Well, that's only going to happen when dy dx is equal to 0. And this fraction can only take on a value of 0 when the numerator is 0 and the denominator is not 0. And so if we set this numerator equal to 0, we end up with this equaling 0, and the calculator's in play, so I used my function mode graph screen to graph this, and I found when that graph was equal to 0. That graph was equal to 0 at 2.208, and that's going to be the time when the object has a horizontal tangent line up against its path. It does go on to say, is the direction of the motion of the particle toward the left or toward the right at that time? Give a reason for your answer. Well, what I went ahead and did at that time is I found my velocity vector at 2.208, and if I put 2.208 into dx dt, I got 0.416, and then we know what we're going to get when we put that into the spot for the y component of velocity. It's going to be 0. That's basically how we determine this value, by setting dy dt equal to 0. So here's the velocity vector at time 2.208. Well, since the x component of velocity is positive, that means the x coordinate of the object is increasing, and that means the object is moving to the right at that time. And then the last piece here has actually 3 pieces within it. Tells us there's a point with x coordinate 5 that the particle is going to pass through twice, and then we want to find the things that they ask us to find. The first of which, the 2 values of t when that occurs. So what 2 values of time is the x coordinate of the particle going to be equal to 5? So basically you've got the formula for the x component of position if you just set that equal to 5. Now I did this with a graph, just because the calculator was in play, so I went ahead and said, well, if I'm going to solve this, I can graph this real quickly, graph this, find the 2 intersections. This could have been easily solved by factoring too, right? Subtract the 5s, have a 0 here, factor, and you'll get these 2 times as the times when the x component of the position of the particle is 5. Then goes on to say, we want to determine the slopes of the line tangent to the particle's path at that point. Now this is kind of weird. We don't really have the capability of graphing the curve that the object's traveling on, right? Because we only know dy dt, and this is, although we can try to find an antiderivative of this, we could try to use integration by parts to try and produce an antiderivative of this and work backward to the function. We aren't going to really want to waste the time to do that, but what's kind of weird, since it passes through this point twice, it's going to be at 2 different values of t, and we're actually going to get 2 different slopes as we pass through that point. So the first time that we pass through that point is at a t value of 1, and the slope of the line tangent to the particle's path at that time, just like we did in part C, dy dt divided by dx dt, but evaluating at 1, and then evaluating that on the calculator is going to give us 0.432, and then evaluating that at 3 is actually going to give us a pretty nice answer of 1. But again, you can evaluate that on the calculator. So 2 different slopes as we pass through that point, so kind of a weird situation. We pass through the point twice with different slopes at the 2 different times. And then the last piece here, the y coordinate of the point at that time, right, or at that x value, given that the y coordinate of the object at 2 is this ugly value. And so if we're trying to find the y coordinate of the object at 3, what we can do is we can start with the y component of position at 2, which is 3 plus 1 over e, and we can add on how much the y component of position changes from 2 to 3 by integrating the rate of change of the y component of position, which is the y component of velocity. And so if you do this computation on the calculator, it actually works out pretty nicely. You're going to end up with a y coordinate of 4 that corresponds to this x coordinate of 5.